Good morning, sir. Neeraj, sir, it is audible. Neeraj, sir.
Yes, you are audible. Yes,
Neeraj,
you are
sir, we
audible.
can. Neeraj, sir, we can wait for a few minutes. Actually, participants are joining the link and the session, as it is the weekend, so they may be taking some time to join. So just wait for few minutes, 2 3 minutes, then we will be starting. Neeraj, sir, please check your mic. Neeraj, sir. Neeraj, sir, your voice is not audible. Can you check your mic? PPT is visible, but I request you to kindly check your mic.
Hello, Vishal sir.
Sir, good morning, sir. Yeah, your
Yes, sir.
sound is now.
Audible, sir. Audible.
Okay, okay, thank you. So, shall we start or we should wait?
I think, sir, we can start. Uh, some of the participants have already joined, and a few may join in between that. It's okay, sir. We should start because time is already 9:10, so we should start, I think.
Okay, okay, thank you. So, good morning to everyone present in this session. I am Dr. Niraj Kumar Chaudhary, currently working as an associate professor in the Department of Electrical Engineering, MNNIT Allahabad. So, before I start my talk, I first of all wish you all a very happy Dhanteras and happy Diwali in advance. So, my talk will be basically related to the protection challenges in a microgrid, or you can say that in a distributed generation based power system. What are the different possible consequences on the performance of the protection coordination that we are going to see, and how the different mitigation schemes can be implemented to improve the grid resilience and the stability of the overall system. So that I'm going to share with all of you in this session. So before I start, just in the introductory remark, I would like to mention that uh, all of you know that nowadays the use of renewable energy sources in the form of distributed generators are getting very popular, right? So because of the implementation or integration of DGs in the system, the utilities are nowadays moving ahead towards the concept of microgrids or smart grids. Uh, that is very much essential if we look at the future prospects of the modern power system. Then, to achieve the goal of net zero carbon emission, the role of these distributed generators and microgrids is very much essential, right? So, in this session, we will discuss about the protection coordination of microgrids, various challenges, and the different schemes available that are already used, and for some research ongoing works that we are going to discuss in this session.
Good morning, sir.
Good morning. Okay,
Good
so
morning, sir.
this is the outline of the presentation. I hope you can see the slides. Is it visible? Slide number 2, outline of the presentation.
Sir, please keep it in slide
Visible,
mode,
sir.
sir.
Okay. In my system, it is already in the slide mode, but again, I will do it.
It's okay, sir. Continue, please.
Can you see the full screen now?
Actually, not, sir. But it is okay, sir. It is clearly visible. It's okay, sir. Please continue, sir.
Okay, okay. So this will be the outline of this presentation. First of all, we will discuss about the DZ integrated distribution networks, followed by the introduction and evolution of the microgrid system. Then we will see that what are the possible protection challenges that may occur in the system after the integration of the DZ, and how the integration of the DG impacts the system stability. Here, when I talk about the system, it means that the complete microgrid system, right? Later on, we will see that what are the different types of standard as well as user defined relay characteristics available in the literature, and not only literature, the modern relays that are being used by the utilities nowadays. So different standard relay characteristics are there. If you will see the IEC 60255 characteristics or the IEEE standards. Therefore, some relays are modified also, named as user defined relays. So that is modified as per the requirement of the utility system, means depending upon the load requirement or the type of DG connected to the system, the characteristics of the relays are modified. That we will see the application of such relays, we will see in the coming slides. And after that, I will showcase one of the examples where I have considered a 7 bus microgrid system and how the protection coordination problem has been formulated in that test bed system, and how the optimal settings of the relays along with the total operation time of the different relays are calculated with the help of few optimization technique that we will see. And at last, we will see the conclusion and some future scope of works that can be done by the researchers in this area. So before we proceed further, we can see in this slide, slide number 3, about the evolution of the protection coordination schemes. You can see that relevance of this topic, that is protection coordination, in terms of number of publication in the past few years, where different type of protection coordination schemes has been used, starting from the conventional protection devices, then adaptive protection schemes, then multi-agent based systems based protection schemes, data mining based schemes, blockchain based protection schemes, and user defined characteristics based protection schemes. So you can see that among all these protection schemes, the number of publications in case of user defined relays is continuously increasing. Means here you have a flexibility, because you have a flexibility to adapt with the system configuration. You can modify your relay characteristics as per your requirement, right? Then here you can see the basic in the introductory part. You will see that what is actually this DG based system and microgrids. I hope that in a sequence of lectures or sessions in this faculty development program, you have already gone through the concept of microgrids and distributed generation based system. But here in brief, I want to summarize once again that all the DG based systems are not actually microgrid. That all of you know, I hope. There are certain features of a microgrid. That one of the key aspect for the microgrid operation is that it can operate in both grid connected mode and islanded mode of operation. Right. So the main advantage is that suppose if you have a fault in the upstream network, upstream network means that in the side of grid, utility grid, if you have any fault in the system, then your microgrid will be isolated from the upstream network, and it may operate independently from the utility grid. So due to this feature, key feature, the overall reliability of the power supply system improves. Means ultimately your system is becoming more resilient, right? So here in this figure we can see that you have different type of generating stations along with the different type of loads, starting from domestic loads to the industrial loads. Then you have different type of renewable energy sources. Hello.
Hi, yeah, we can see only one slide, your outline. We cannot see any diagram or anything.
Okay. Then there is some problem. I think let me share my screen again.
Just close the slide and again open.
Yes, let me again share it.
Sir, once stop sharing and then reshare so that it may be resolved.
Sir, now it is visible, sir.
Visible. Sir,
Okay,
I request you to
thank
kindly
you.
once again go through from your third slide. Sorry.
Okay, okay.
Please, sir. Thank you, sir.
So after this outline slide, I was discussing about the relevance of this topic. It means why I have chosen this topic for this particular session. That you can see that different types of protection schemes has been implemented. Uh, you can see the trend of the protection schemes being implemented by different researchers in terms of number of publication, year-wise number of publication. So here you have different type of protection schemes like conventional protection scheme, adaptive schemes, multi-agent based schemes, data mining based, blockchain based, and user-defined protection coordination schemes. So you can see the popularity, or you can say the need of this user defined protection coordination schemes in microgrid in terms of number of publication year wise. You can see there is a uh, uh, increase in number of the publications. So the main reason is that the power system is continuously changing day by day. Means every day there is some advancement in the power sector, and mainly in terms of the integration of different type of renewable energy sources. And when you are going for the integration of DGs at such a mass level, then there is a topological change in the system, which needs that your protection schemes as well as systems should be adaptive in nature. Means with the addition of individual source, you will have increased fault current level in the system. So you need a protection scheme where you can adjust the parameters of the relays as per your requirement and the system configuration, right? So now in the next slide, uh, slide number 4 is visible or not? Can anyone confirm?
No, sir. No, sir.
No, sir.
Just a minute.
So share entire screen, sir. In option of sharing, choose the option entire screen.
Yeah, I have done that only, but let me try it again from my mobile phone.
Yes, sir. Keep it like this only. Sir. Now it is okay, sir. Once try to change the slide, we will confirm whether it is changing or not.
Okay, 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 okay. So now here in this figure two, you can see a DG based system and the microgrid. Earlier, I was saying that all the distributed generation based power systems are not classified as a microgrid because there are certain features that must be fulfilled before it is called as a microgrid system. The one of the main key feature is that the ability of a microgrid that enable it to operate in both the modes of operation, that is your grid connected mode of operation and the islanded mode of operation. So the basic difference is that whenever there is a fault in the upstream network, means at the higher voltage side of the network, that is towards the utility grid side, then one of the essential requirement for the microgrid is that it should isolate itself from the upstream higher voltage networks, right? So that the fault cannot be propagated in the microgrid side, right? So that mode of operation is known as islanded mode of operation. Now, what is the basic difference that we need to understand? If the mode of operation changes from grid connected mode to islanded mode of operation, then basically this is a topological change. So with every topological change, there will be change in the fault current capacity or fault current contribution in the network. Now you know that the protective devices mainly works uh, on the basis of current magnitude. If you talk about the low voltage or medium voltage network, then mainly the overcurrent protection schemes are used, as especially at the medium voltage and the low voltage network, in the form of overcurrent relays. So if the current contribution changes, then the settings of the protective device need to be changed. So your protection scheme should be adaptive to all the topological changes that may occur in any microgrid system. So here through this diagram, we can see that here we have considered a standard 9 bus Canadian benchmark system where different type of renewable energy sources like your solar photovoltaic based DG, then your wind turbines are also there. Hydro turbine based DG is also installed. EV charging stations are also there. Some storage in the form of battery energy storage system is also present. And this system means the PCC bus you can see here. After the PCC bus, you have a microgrid infrastructure, and in the upstream side you have the utility grid network, right? Now this operation of this circuit breakers enable it to operate either in the grid connected mode or in the islanded mode of operation. So this is one of the basic diagram of a microgrid system. Now in this slide uh, I will show you about the basic evolution of microgrid system. Here we can see a conventional distribution network where you have a radial feeder based system, and the only source of supply is your utility grid present in the system. So here the power flow is unidirectional in nature, starting from the utility grid towards the different feeders it will be distributed. So this is the structure of a conventional distribution system. Now moving ahead, the next advancement in the evolution of microgrid is the addition of different type of DGs. Like here you can see that compared to the previous distribution system, here these 4 DGs are connected to the system. Now out of these 4 DGs, 3 are your power electronic converter based DG, like electronically interface DG you can say. That may be either solar photovoltaic panels or fuel cells or wind turbine based DGs. And the fourth one is your directly interface DG. Means it can be directly integrated to the system after fulfilling the requirement of synchronization issues, right? So here DGs are connected to the system, but here also we cannot say that this is a complete microgrid system, right? Now, third advancement is the provision of protective devices. Means all the protective devices. Here you can see that the blue blocks, these square blocks, represents your circuit breaker along with the relay combination. Then all the circuit breakers and relays should be coordinated with each other. Means they should have a communication between each other. Means suppose a fault takes place on any particular feeder, then the information of that fault should be available to the other relay and circuit breaker in the system also. That's why I have mentioned it as the that there should be a coordination among the different relay and circuit breaker present in the system. Now, the final advancement is in terms of your microgrid control and protection unit, that is a centralized facility. Basically, it is a system that may use any microgrid controller along with some hardwares to manage a microgrids operation that should ensure the safety, reliability, efficiency by monitoring all the control parameters, power flow, frequency, and voltage profile of the system. Right. So there should be a central microgrid control and protection unit that is must for the reliable operation of any power system. Suppose, for example, the input means fuel input to any renewable energy type sources present in the system decreases, then it is obvious that the power generated by that particular DG will decrease. So that DG, which was earlier fulfilling a certain amount of load demand, will now not be able to fulfill that much amount of the load demand. So that information should be shared with the microgrid central control and protection unit, such that the load demand to that particular feeder can be fulfilled by the nearby DG present in the system. So this was all about the evolution of the microgrid system. So now, till now, we have discussed that there are various advantages offered by the microgrids or DG-based system in terms of system reliability, efficiency, uh, then your power loss reduction, voltage profile obviously will improve where you will connect the DG in the system. Power quality enhancement will be there, and of course, if you are able to fulfill the load demand at the local level with the help of distributed generators, then there will be no need of additional transmission line installation in the system, because you are generating the power at the point where it is required, means at the low voltage or medium voltage network. But there is a saying that nothing comes for free. So along with the several positive impacts, you have obviously certain challenges. So these challenges are basically the operational challenges, such as you can see the increase in the fault current levels. Then you may have the bidirectional power flow in the system, which may cause different protection coordination challenges in terms of blinding or protection or false stripping of the uh, certain part of the system. Then there may be problem of you can say unintentional islanding problem may be there. So all these limitations or issues may lead to the reduction in the reliability of the system as well as efficiency of the system, because you know that for any efficient protection scheme, there are certain key features that must be fulfilled, like speed of operation of the protective device, then selectivity, sensitivity. Your least part of the affected system should be isolated from the remaining healthy system. So all these are the possible consequences that may arise due to the integration of DG in the system. So out of the different challenges, I have considered the protection coordination challenges. That is the coordination issue that may arise between the operation of the overcurrent relays, directional overcurrent relays in the system after the integration of the DG. And we will be discussing these aspects only in the coming slides. So here in this diagram, figure 3, you can see the different possible protection challenges in a distributed generation based system. Means suppose here in figure C, you can see that this is one of the example of fault stripping. Means if you have a fault F present in the system, then what will happen? What should be the desired objective of any protection scheme, efficient protection scheme, if the fault occurs at F? Then it is desired that only the faulty section, that is the line between the bus 1 and 2, should be disconnected from the system uh, by the operation of relay R2. If R2 senses this fault and send a command to the circuit breaker associated with R2 that there is a fault nearby this relay R2 on this particular feeder, so it should ideally isolate it. But now, what is the problem in this case? You have a DG connected on the other feeder at any node of the other feeder where the fault has not actually occurred, right? So along with the utility grid here, you have a DG connected to the system. So if the fault F occurs here, then there will be two sources for this fault, one from the utility grid side, that is represented by IF grid, and another from this DG, that is IFDG, fault current supplied by the DG. So what will happen if this IFDG, that is fault current provided by DG, exceeds the pickup current of this relay R1, then what will happen? This relay will sense this current as a fault, and ultimately your healthy feeder may get isolated from the system. So this is one of the case of maloperation of the relays, that is your false tripping of a feeder on which actually the fault has not occurred. So similarly, there are other in the other figures you can say there are problem with the reclosure and relay coordination. Then you may have problem with the reclosure coordination. So all these are because of the integration of DG in the system, right? So these are the possible protection coordination challenges. So I hope you are aware about this coordination. Before we go into the detail of the relay coordination problem, you should know actually about what does this coordination means, right? So on the occurrence of fault, there should be a particular sequence of operation among the different protective devices in the system. This is very basic part, but let me recall once again that suppose if you have a system and fault occurs in that system, then actually there are different layers of protection. So the very first layer is provided by the recloser if present in the system. Means reclosures basically the operation of the reclosures are similar to circuit breakers, you can say, having different duty that if any disturbance and or fault occurs in the system, then recloser will open and close its contact for few electrical cycles. So if that disturbance or fault is removed automatically from the system by any means, if it removes, then it means that that was not actually a fault, that was the transient present in the system, and the system will operate in a normal mode, right? But if after few cycles the fault is not cleared, then the layer of protection will be provided by your relay and circuit breaker combination combinedly, right? If you have fuse present in the system at lower voltage networks, then again there are some characteristics, operating characteristics of fuse, like minimum melting characteristics, MMT characteristics, then TCT characteristics, total clearing time characteristics, right? So all depends upon the type of protective devices in the system, as well as the uh, different type of uh, systems, like what type of DG connected to the system, right? That we will discuss. Again, in this slide number 11, we can see that uh, you have a radial system in which DG is not connected, and the same system where DG is connected at any bus number A or node A. Then for the first system, that is figure 4.1, suppose if fault occurs at any point here, means after relay R1, means before this load L1, if fault occurs on this line, then there should be some primary relay associated with that fault, and there should be backup relay. If in case the primary relay fails to operate, then backup relay should come to the picture. So that's why here in this time versus current characteristics, IDMT characteristics, you can say you can see that the time of operation for this relay RA is below the time of operation for the relay RB, right? Another important thing is that all the coordination, that is coordination between any protective devices, should be defined for a particular range of the fault current, that is the minimum and maximum level of the fault current. So here you have this line A and B represents the minimum fault current and maximum fault current that may occur in this system. So this magnitude of minimum and maximum fault current basically depends upon the system configuration as well as the type of fault present in the system. So first of all, you need to determine these two range of fault currents, and after that only you can define your relay coordination problem. So always the time of operation of the primary relay should be lesser than the time of operation of the backup relay, and there should be a time margin, discrimination margin between the operation of these two relays. Now, what is the problem after the integration of DG? If you have integrated DG at bus number A, then you can see that earlier when there was no DG, then suppose this one was the value of the discrimination time margin, which is also known as coordination time interval, that is CTI. Now, when you have connected DG, then what actually happened? Now there will be increase in the magnitude of the fault current. So whenever there will be increase in the magnitude of fault current, then as per the IDMT characteristics of the relay, the time of operation of the relay should be lesser for increased level of fault current. So that's what we can see, that the time discrimination margin, that is CTI, is continuously decreasing as your fault current is continuously increasing. So if further the penetration level of the DG in the system is increased, maybe either by addition of another DG or increasing the capacity or size of the DG connected to the system, then there may be a chance that these two characteristics of primary and backup relay may overlap with each other. And even in some cases, the time of operation of the backup relay will be more than the time of operation of the primary relay. So in that case, this is a violation of the relay coordination, that your backup relay and primary relay, backup relay operates prior to the primary relay operation. That we will see in the result section. Now here, I would like to introduce some other challenges that may occur in any microgrid system, because as we have discussed in the architecture part of the DG microgrid, that there may be multiple type of DG connected in the system. Some DGs may be directly interfaced or synchronous machine based DG, you can say SBDGs, and most of the DGs are your electronically coupled or inverter based DG. So SBDGs have a significant impact on the transient stability of the system. So this transient stability, you also know it as rotor angle stability. So in this figure A, uh, this figure shows that in a system integrated with your SBDGs, the transients occurring under the faulty events may cause a loss of synchronization of the system, right? So suppose now there are two chances. If the fault is a minor fault, means maybe like transients, then normally the stability of the system, transient stability of the system is retained because of the higher inertia of the system. Means if you have SBDGs mainly connected to the huge interconnecting network, that is your power system network, then there is huge inertia of the rotors in the system. So for they tolerate or sustain the smaller disturbances, minor faults occurring in the system. However, suppose if there is a major fault or critical fault occurs in the system, like you know that the most severe fault in the system is the three-phase bolted type of fault. Means when I say bolted fault, then it means that your fault impedance is ideally zero, right? So in this case, in case of major faults, you can see in this figure 6b that the rotor power versus rotor angle characteristics, you can see in this figure 6b, and you all can observe that the system in this case operates at reduced power level, right? You can see that the three curves are drawn here. That is your first one is the basic one, this dotted power versus rotor angle characteristics, which is for the condition when there is no fault in the system, means normal operation of the during the normal operation of the system. Then when during the fault, what happens, the power contribution decreases. So this was the characteristics. Now post fault means just before the, or you can say that when the fault is about to be cleared from the system. So the modified power versus rotor angle characteristics is now DEF. That is, the system is now operated at a reduced power level. And if the fault is not cleared before the critical clearing time, there is a key word especially in terms of microgrids having high penetration of SBDGs in the system. So if the fault is not cleared before the critical fault clearing time, then what may happen? Your system may become unstable, right? So this is important term. And whenever such condition arises, or whenever there is a high penetration of SBTG connected to the system, then the inclusion of this CCT, that is critical clearing time, is very much important, and that should be incorporated in your relay coordination problem. Means here you can see that this is the expression of critical clearing time, that is TCCT. Now there are, it depends upon different factors like your H, that is the inertia constant of SVDGs. Then your PM naught is basically the mechanical power input to the machine. Then F is the frequency of operation. Delta naught is your initial power angle, and delta critical CR is your critical power angle, right? So here in third equation, you can see that this TPRIM basically is the time of operation of primary relay, right? We have seen in the previous few diagrams that there was some primary relay in the system and some backup relay in the system. So on the occurrence of fault, the time of operation of the primary relay plus the time of operation of the circuit breaker should always be lesser than the time critical clearing time, TCCT. Otherwise, your system may become unstable. That's why I mentioned that while formulating your relay coordination scheme, the following constraint of CCT, that is critical clearing time, should always be incorporated in the system, right? Now, another aspect is the voltage stability and low voltage ride through capability of your DGs connected to the system. It is also one of the crucial challenges faced by the power system operators, that is the utility side. So, in a DG integrated system, that is your microgrid system, this is one of the key aspects that should always be considered, because it is not desired that whenever a fault occurs in the system, then DG gets isolated from the system. Because whenever there is a isolation of any power source from the system, then what is the problem? Ultimately, your load demand may not be fulfilled if the power sources are disconnected from the system, right? So during faults also, DG must remain connected to the grid, microgrid you can say, for a specific time, right? So this time duration basically depends upon the magnitude of the PCC bus, right? So here in this figure A, you can see this is the PCC bus, means the point of interface of the utility grid and the microgrid system. So here you can see that the PCC bus, voltage of the PCC bus, the range is shown like that. If it lies between 0.88 to 1.1, then there will be continuous operation. It means there is no fault in the system. There may be, if it is slightly below unity, 1 per unit, it means that load may have got increased in the system, due to which there is some voltage drop in the system. And if the load decreases, then there will be a voltage swell condition, means above 1 per unit condition. So there will be continuous operation of the DC. Now when the voltage is in the range of 0.7 to 0.88 per unit, then this is the derived expression of the time of operation, that is TLVRT, means it is 0.7 plus mentioned in here. So whenever you are calculating actually the time of operation of the relay, then you will have to add the TLVRT, calculated TLVRT, with the time of operation of the primary relay, right? So that will be basically the total time of operation taken by the relay to sense that particular fault, right? Now, here another thing is that uh, if the voltage is in between 0.5 to 0.7, then the overall time of operation will be T relay plus 0.16, means your DG should be disconnected from the system if the time of operation is equal to or above this value T relay plus 0.16 second. And then as per the IEEE standard 1547, DG should be disconnected from the system immediately if the voltage of the point of common coupling bus falls below zero point 0.5 per unit, right? So this is another important factor that should be considered while solving the relay coordination problem. Now, after discussing the challenges associated with the voltage stability and transient stability condition, another challenge is faced by the protection coordination schemes is due to the change in mode of operation of the microgrid. That is transition in the operation mode of microgrid from grid connected to islanded mode. Now, what will be the problem in this condition? Suppose if your system is operating in the islanded mode of operation, then the objective of any utility is to protect the system uh, during faulty condition in that particular mode of operation, right? So accordingly, you will calculate the relay settings depending upon the fault current in the system, right? So it has been observed that when the relay settings obtained in the grid connected mode of operation is tested for the relays in the grid connected mode of operation of the system, then there are several constraint violation. Obviously, there will be several constraint violation because in both the cases, the fault current is different. In the grid connected mode, you have grid present in the system along with the different distributed generators. So due to the variation in the magnitude of fault current, there will be obviously change in the time of operation of the relay as per the IDMT characteristics of the relay that we have seen in the previous slides. So same problem has been observed that when you have calculated the setting of relays, that is your time multiplier setting or current setting of the relay, then that will be valid for the grid connected mode of operation only. If you will replace or put the settings obtained in the grid connected mode to the islanded mode of operation, then again there will be some constant violation. So the solution is that you need to combine the different constraints of grid connected mode and islanded mode, and accordingly you need to calculate the common optimal settings that should be valid for both grid connected mode of operation and islanded mode of operation of the microgrid. Means I want to say that here in this previous figure, as we have seen that there was a problem with the coordination of relays when the mode of operation of the microgrid changes from grid connected mode to islanded mode and vice versa, right? So there may always be a change in mode of operation because you don't know about the behavior of the system, how it may behave depending upon the fault in the system towards the upstream network or the downstream network. There may always be a change in the mode of operation due to the transition from grid connected mode to islanded mode. So it is not a good option that isolate you need means in isolation you calculate the relay settings for individual mode of operation. So there should be a common optimal setting that should be valid for both the mode of operation, right? Now, after the mode of operation of microgrid, the performance of the protection coordination scheme also depends upon the different type of relays as well as its characteristics, right? I will show you in this slide the two basic characteristics. First one is the standard characteristics. Here you can see this is the standard relay characteristics as per IEC 60255 standard. The three characteristics are normally inverse, that is Ni, then your very inverse, then third one is extremely inverse. So as you will move away from normal inverse towards extremely inverse characteristics, you can see that the time of operation decreases. Means for the same magnitude of the fault current, suppose if the uh, multiples of pickup current, that is your in terms of current setting, if it is at 10, then for this particular value, you can see that the time of operation for this red curve that basically represents your extremely inverse characteristics is least, followed by the very inverse and then normal inverse characteristics, right? Now, in the figure B, you can see this is a dual setting directional overcurrent relay. The first one was your conventional directional overcurrent relay, means it will operate only in a particular direction of fault current when it is flowing in a particular direction, either forward or reverse direction of fault current. But this is one of the user defined relay characteristics, dual setting relays. Means as the name, from the name itself, you can see that dual setting means it has two settings, a pair of setting. Means one is for the forward direction and another for the reverse direction, right? Means if suppose there is a relay R1, then the relay R1 will have a particular TMS and PS setting, means time multiplier setting and plug setting for the forward direction of fault current. And similarly for the reverse direction of fault current, for the same relay R1, there will be TMS reverse as well as PS reverse. So similarly for the three type of characteristics, normal inverse, very inverse and extremely inverse, you can see the different IDMT characteristics. Here in this slide, you can get better insight to this problem about the two type of characteristics. In figure A, where the conventional directional overcurrent relays are used, suppose if fault occurs in at any point L1 in the system, this is the faulty line, means when the faulty line is L1, then what should be the primary relays? Primary relay, suppose if the primary relay is R1, then which relay should be the backup for this primary relay R1? R5 will be the backup relay because these are directional overcurrent relay, right? If you will, you cannot consider R4 here because always the settings are defined, settings of the relays are defined, moving away towards the bus to which the relay is connected. That's why you can see that these are the directions mentioned. These direction represents that these particular relays will work only if the current will flow in this particular direction towards the direction shown here, right? So for the fault at this line L1, in this R5, you have the current flowing in the same direction as it is flowing through the relay R1. That's why R5 will be the backup for relay R1. Now, if for the same fault location, relay R3 is considered as the primary relay, then using the same principle and concept, you can see that R6 will be the backup relay for this relay R3. Now, similarly, for different fault locations on line L2 and L3, you can prepare or formulate this primary and backup relay pair. So this is for the conventional directional overcurrent relay. Now, suppose in this figure B, where we have replaced the conventional DOCRs by dual setting DOCRs, that is dual setting directional overcurrent relays. So you can see that there are two arrows mentioned above each relay, right? R1, above R1, you can see two arrows. So this relay, it means that this relay will sense the fault for both the direction of current, right? That is forward direction and the reverse direction, right? So for the same fault location at L1, if R1 is considered as the primary relay, right? Then what will be the backup relay in this case, in case of dual setting DOCRs? R2. Why? R2 in the reverse direction. Earlier, I have told you when I was showing the characteristics that each relay will have a pair of setting, one for the forward direction of fault current, another for the reverse direction of fault current, right? So you can see that if fault occurs at R1, L1 on this line, the same fault location, and you have considered R1 as the primary relay, then R2 will be the backup relay. And if R3 is considered as the primary relay for the same fault location, then R4 will be the backup relay, right? So this is one of the change due to which the overall time of operation of the relay after the occurrence of fault reduces in case of dual setting directional overcurrent relay. That you can observe, means later on you will see in the result section that what is the comparison between the time of operation of the dual setting DOCRs and the conventional DOCRs. So what we have seen that as the relay characteristics changes from normal inverse to very inverse and then to extremely inverse characteristics, then the time of operation will change, time of operation of the relays will change, and ultimately if time of operation is getting changed, then your fault detection time is getting changed, right? And if fault detection time will change, then fault isolation time will increase or decrease, right? So the possible solution again is that you need to calculate the common optimal settings of the relay for both the modes of operation of microgrid, considering the mixed inverse characteristics. Means in the previous slide, in one of the proposed solution, we have discussed that common optimal setting of the relay should be obtained considering both islanded mode and grid connected mode. Now, additional change is that you have different type of relays present in the system having different type of characteristics like Ni, Vi, Ei. These are standard characteristics, right? So suppose if any utility is has incorporated normal inverse relay characteristics, then the total time of operation of the relays will be different. Now the utility, if need to replace those relays by Vi characteristics, then again there will be different time of operation sensed by the relays. Fault sensing time will be different, and same for Ei. So the proposed solution is that you consider this characteristics also as a decision variable while formulating the relay coordination problem, and you need to optimally determine these characteristics, that is the type of characteristics that should be used in any particular system, right? So along with the two decision variables, that is your TMS, time multiplier setting, and another one is plug setting or current setting, this may be considered as a third optimization variable or decision variable of the relay coordination problem. And you need to use the mixed inverse characteristics, that is basically the optimal combination of Ni, Vi, and Ei characteristics, right? So this will give you a better solution to the protection coordination problem for your system. Now, next part is of this presentation is related to some of the basic result that I will show you, and these are basically related to the theory part. Just we have discussed, that is the impact of mode of operation of the microgrid as well as the impact of different type of relay characteristics. I will not go into that much detail of this flow chart. Just you need to do one thing, that first of all you need to identify the mode of operation of the microgrid, that is whether the system is operating in the grid connected mode or in the islanded mode, and accordingly you need to modify your system data for the preparation of the primary and backup relay pairs for maybe conventional DOCR or dual setting DOCR. Here in the coming slides, I will show you the result of detailed result of dual setting DOCRs. And at last, I will show you the comparison between the function on the operation of the conventional as well as dual setting DOCRs. Now, after the formulation of the primary backup relay pair for different fault location in the system, there will be formulation of objective function considering both operating modes, that is GCM and ISM, as well as with the set of characteristics, whether it is normal inverse, very inverse, extremely inverse, or mixed inverse characteristics, right? And after that, you need to when you have formulated your objective function in terms of the total operation time of the relays, and when you have formulated your constraint, you should know that relay coordination is basically a constraint optimization problem, minimization problem, right? The objective function should be minimized, that is, the total time of operation of the relay should be minimized subjected to the fulfillment of certain constraint. That constraint may be your coordination constraint, your constraints related to the operation of the relays, or maybe related to the coordination time interval, or different variables depending upon the type of relay used in the system. And once you have formulated the objective function, then again there is a new area of work. You can use different type of optimization algorithms, hybrid type of optimization algorithms to solve that problem, right? To determine the optimal settings. So here, this is the expression of objective function. In some literature, you will find that they have only considered the time of operation of the primary relay. Here, forward is mentioned that because I have used here dual setting over current relay, right? That's why TOPFOW is your operating time of primary relay in the forward direction for fault current. I have shown you the forward and reverse direction of fault current in the previous slide. And this is your IDMT characteristics of the relay, standard IDMT characteristics. So what we have done here, we have considered different variables like this lambda and eta, both are considered as a variable because in case of standard relays, standard IDMT relays, these values basically depends upon the type of relay characteristics. Suppose if you have normal inverse characteristics, then these have some constant value like lambda is equal to 0.14 and this eta is equal to 0.02. Now, if the characteristics changes from Ni to Vi, then the value changes to 80 and 2. And accordingly, depending upon the characteristics of the relay, the value changes. But as I have considered here the mixed inverse characteristics, then you need to consider these two variables as a decision variables in the protection coordination problem along with the TMS, PS, right? And CTR is your current transformer ratio, CT. So after the formulation of the objective function, you need to define the constraints. So this is the selectivity constraint, that is the constraint related to the coordination time interval. As we have seen in the figure, that time of operation of the primary relay should always less than the time of operation of the backup relay. So the difference is your should be greater than equal to your coordination time interval. Now, depending upon the type of relay used in the system, whether you are using electromechanical relays or you are using microprocessor based digital relays, the value of the CTI changes. Normally, it varies from 0.2 to 0.5 second, right? But you can means adjust its value depending upon the type of relay used in the system. So these are the again the time of operation of the relay in the for the reverse direction of fault current, and the associated variables you can see here. And you need to define the different constraints range, means the minimum and maximum value of the TMS for both the forward and reverse direction of fault current, along with the minimum and maximum value of plug setting for the forward and reverse direction of fault current. And along with these constraints, you have some constraint that is bounds on the relay operating time, means individual relay for individual relay present in the system. There should be a minimum and maximum time of operation for all the relays, right? You need to define these relays as per the system requirements and load connected to the system, right? So here the values that are considered here are shown, that maximum and minimum value of TMS considered is 1.1 and 0.1 respectively, and similarly for PS max and PS minimum 2 and 0.5 respectively. Now the test system considered for this study is your 7-bus microgrid system, which is basically a part of low voltage part of the IEEE 14 bus benchmark system. Means uh, below this transformer, means, or you can say that upstream network of this system is your high voltage section. That's why we have not considered that system for the study of relay coordination problem. We have only considered the low voltage section of the IEEE 14 bus benchmark system. And here we have modified this system as per the connection or integration of DGs. We have integrated two DG in the system and one SBDG in the system at the three suitable nodes. Now, another area of work is where some people are working, means optimal location of DGs in any distribution network, right? So that is another area. But here we have considered the location depending upon the hit and trial method, that after the connection of the DGs at such locations, the voltage profile of the system was best compared to the different locations present in the system, right? Means the detailed system parameters will be shared with you. And we have fixed the relays, different dual setting relays at each line of the system. Means on each line you can see that there are two relays, and all the relays we have considered here as the dual setting relays. Now, after simulating the system, we have calculated the fault current through the relay coils. Actually, you need to calculate the current flowing through the relay coil, because the fault current flowing through a particular line or feeder will be very high. That's why every relay coil is connected across the CT secondary, current transformer secondary, and depending upon the CT ratio, adjusting the CT ratio, you can modify the current that may be allowed to flow through any relay coil, right? So we have calculated the fault current through the relay coils in both the grid connected mode of operation and islanded mode of operation. So you can see that there is a difference in the magnitude of current flowing through the relay coils in both the mode of operation. So in all the cases, you can see that the current flowing through the relay coil in grid connected mode of operation is higher than the current flowing through the relay coils in the islanded mode of operation, right? And based upon the same concept of the formulation of the primary and backup relay pair, we have formulated the relay pairs, different relay pairs. So there are 8 fault locations we have considered, means all the there are 8 lines in this 7 bus microgrid system from L1 to L8. So accordingly, we have formulated the different 22 relay pair, right? For every relay pair, there are primary relay as well as backup relay. Now, after the formulation of the objective function and the associated constraints as shown in the previous slides, we have calculated the relay settings, right? So these relay settings are actually for the standard relay characteristics in grid connected mode of operation by using GWO, Gray-Wolf optimization algorithms. So the values are shown here. And for the calculated optimal relay settings, you can see that the value of objective function OF, how it varies, means for normal inverse relay characteristics, its value is 3.3877 second. Now, as we have replaced all the relays by VI type of relay characteristics, then it comes to 1.6825 second. There is a huge reduction in the total time of operation of the relay, as we have changed the relay characteristics from normal inverse to very inverse. And again, when replaced the relays with EI characteristics, extremely inverse characteristics, then there is further reduction in the total time of operation of the relay, right? This is justified, these results are justified as you have seen in the IDMT characteristics, that for a similar fault current level or plug setting multiplier level, the time of operation for the relays with extremely inverse characteristics was least. Now, here is the actual case where we have considered the relay characteristics as also one of the decision variables. This is represented by relay characteristics identifier RCI, which is basically your optimal selection of the standard relay characteristics, right? Means we have numbered the relay characteristics, 1 for very inverse, 2 for extremely inverse, and 3 for normal inverse. So in this case, there was no selection of normal inverse relay characteristics, and we have obtained this relay settings for mixed type of relays. When mixed type of relays are used in the system, means suppose in our system that we have considered, this figure 14, here you have different number of relays connected to the system. Suppose you have 16 relays here connected to the system from R1 to R16. So now in case of mixed inverse characteristics, it may be possible that relay R1 is suppose a very inverse type relay, relay 6 is suppose normal inverse type relay, and another one suppose R13 is extremely inverse type relay. So all it depends upon the calculation of optimal relays, optimal relay characteristics through this relay characteristics identifier. So you can see that in this case means when the objective function value is calculated with mixed inverse type of relay characteristics, then it comes to 1.6065 second. Means this is the total time of operation of the relays after considering all the possible fault locations and operation of the associated relays. So this is again less than the total time of operation of relay that we have calculated here in case of extremely inverse characteristics. It was 1.6124 second, and here it is 1.6065 second. Now anyone can say that what is the big deal in that? Here you are getting 1.6124, here you are getting 1.6065. The magnitude is not that much different, but it is very much significant for this particular problem, because you know that practically the relay operations time on the occurrence of fault should be in millisecond also sometimes, right? That's why it is that much of relevance. Now, depending upon the calculated value of the uh, relay settings, we have calculated the associated time of operation of the relays by putting the value of TMS, PS, and the relay characteristics identifier in the individual equation. You can see that the first figure, the upper one, here for all the primary relays having when having NI characteristics, VI characteristics, EI characteristics, and mixed characteristics are used, then this is the time of operation of the relays. Here some overlapping is there, that's why you are not uh, I don't know you are able to see it or not, but there is a difference in slight difference in the magnitude of time of operation, right? Then this is for the backup dual setting relay time of operation. Here in the first one, you have seen that in seconds, when NI characteristics was used, then the time of operation was somewhat in between 0.2 second and 0.25 second. Now, for the same fault location and the relay pair, means the backup relay time of operation you can see is around 3.5 seconds. So now you can calculate depending upon the time difference between the operation of the backup relay and the associated primary relay. You can calculate the CCT or MCT, measured coordination time, actual measured time, coordination time interval by subtracting backup time of operation and primary time of operation of the relay, and the MCT values are calculated for different type of relay settings. Relay characteristic curves. Now, earlier the tables and the results were shown for the grid connected mode of operation. Now, these are the same results for the islanded mode of operation. Here you can see that the same study has been performed for a microgrid, same microgrid system, that is 7-bus microgrid system. considering the islanded mode of operation. And the total objective function value you can see in this table 4. It varies from 3.9882 second to 1.6928 second as the relay characteristics changes from Ni to Ei. And similarly, with mixed inverse characteristics, we have optimally determine this relay characteristic curve using RCI as a decision variable, and we are getting the total time of operation of the relay, that is the value of objective function, as 1.6345 second. Again, less than the total time of operation in case of Ni, Vi, and Ei characteristics. What does it mean? It means that your mixed inverse characteristics of relays are providing you a better result in terms of the total time of operation of the relays. What does it mean? It means that if you will use the mix inverse characteristics, then the fault will be cleared in lesser time of operation, right? And similarly, the time of operation of the primary backup relays and the measured coordination time interval is obtained as shown in the three figures. So here is a summary in terms of the constraint violations when you have used the different type of characteristics like NI, VI, EI, and mixed inverse characteristics. So for islanded mode, when you have determined when we have determined the characteristics, then the settings of the relays when placed in the grid connected mode. So these are the number of constraints that we observed to be violated. And similarly, the relay settings obtained in case of grid connected mode, when that is placed in the islanded mode of operation of the microgrid, then these are the number of constraints that were observed to be violated, right? So the proposed solution, as we have seen in the flow chart and diagrams, that you need to calculate the common optimal relay setting of the relay, again by considering the different mode of operation of the microgrid. So here we have calculated the relay settings, that is TMS, PS, and the optimal selection of the relay characteristics, and based upon that, the total value of the time of operation of relay calculated is 1.68 second, right? And these are the relay operating times, operation time of the your relays by using this two types of optimization algorithms, that is your gray wolf optimization as well as your genetic algorithm optimization. So in this case, in this particular case, you can see that in the grid connected mode for the primary relay, the time of operation is shown by the blue curve. Then grid connected mode backup relay time of operation is shown by this red curve. And the measured coordination time interval is the basically difference between the time of operation of the backup relay and the primary relay, that is shown by this golden or yellow curve, you can say that. And similarly for the islanded mode of operation, here it is shown, right? So A, B are the results of the GW, and C and D are the results provided by the genetic algorithm. So this is the overall comparative analysis of the study that I have shown you in the slides of the result and discussion slides. For the grid connected mode and islanded mode, for conventional type of DOCR using GA and GW, and for dual setting DOCRs, the results obtained using GA and GW are shown, and accordingly the percentage reduction in the total operation time has been noted here. So you can appreciate the performance of the mixed inverse characteristics as well as the performance of the common optimal setting of the relay when you will compare it with the conventional DOCRs and using the NI, VI, and EI characteristics. The percentage reduction has been shown in this table. So now I would like to conclude this talk, as we have seen that DG has a significant impact on the performance of the distribution network. Then we have discussed that the operating modes of microgrid uh, have several challenges and consequences on the performance of the protection coordination schemes. Then type of relay and selection of the relay along with the characteristics also impose several challenges on the performance. That's why you need to calculate the common optimal settings of the relay considering the grid connected mode and islanded mode capability, right? As well as the optimal combination of different type of relay characteristics, right? And also we have seen that the solution to the protection coordination problem also depends upon the performance of the optimization technique, right? So this is another important area where so many people are working. Means upon the selection of the optimization technique, which technique will give you better relay setting and lesser total time of operation of the relays. So all the parts that I have shown you in this in my presentation are from these two journal papers, which are of my PhD students. That was published in 2024 and 2022. So thank you. If you have any question, uh, I will take it. I will be happy to discuss it with you. Any
Thank you,
question
sir.
from you?
Thank you, sir, for this insightful lecture and session. So, any participant would like to interact with our expert or have any query or they want to discuss something, they can unmute yourself and they can interact. Any participant would like to interact, they can interact with our expert. So, thank you, sir.
Thank
On
you.
behalf of organizing committee, as you are also the member of the organizing committee, uh, and and on behalf of all the participant, I really thankful to you that you have contributed for the success of this faculty development program. And
Thank you for the opportunity, Vishal sir.
so, with these words, I formally declare the completion of this particular session. And now I request every participant to kindly join us again at 11 a.m. for the next session. So, thank you, everyone.
Thank you, Vishal sir. And happy Diwali to all the participants.
A very happy Diwali to all of you.
Navneet, you are online. Navneet.
Yes, sir. Good morning, sir. I am online, sir.
Okay, good morning. Let me know that which one of, I mean, I will change the speaker. So you let me know that which one is clear. Okay.
Okay.
So right now this is one version.
Yes, sir.
Yeah, previous
Yes.
one was. Hello.
Hello, sir.
Yeah. So this is clear or previous one was clear?
Actually, sir,
Hello.
previous one I cannot hear. This is okay, and previous one, sir, can you do it once more?
Okay. This hello.
Hello, हाँ sir.
Navneet.
This is previous one.
This is clear.
Yes, sir.
नहीं ये वाली क्लियर है कि इसके
हाँ
पहले
सर.
वाली चलिए फिर से करते हैं ये दिस इज फ्रॉम द लैपटॉप माइक्रोफोन ओके
Yes, sir. Yes, sir. दूसरी
क्लियर
वाली
प्लीज
या सर दूसरी वाली आवाज.
इसके पहले वाली क्लियर थी इसमें कुछ ब्रेक भी हो रही है शायद
सर पहले वाली मैं
हाँ अभी क्लियर है
पहले सर हाँ ये तो
हेलो
क्लियर है सर.
ये वाली
हाँ
क्लियर
सर
है
ये
ना
क्लियर है.
ठीक है ठीक ओके
ओके सर.